So good afternoon, everyone. My name is Chen. I'm from UC Riverside, and I'm the first author of this Concolic execution paper. This is a joint work with Seoul National University and KAIST. So first of all, this work concerns about Concolic execution. So let's just have a quick recap. So giving a concrete input, the job of Concolic execution is to explore all the alternative execution paths. So the execution, the Concolic executor maintains a concrete state and a symbolic state, and updates both states along the execution. So whenever a branch condition is met, the Concolic executor tries to flip the target branch by constructing the formula and asking the constituent solver to generate the input that can explore the opposite direction of the target branch. So in this case, we generate two test inputs, and together with the original input, we can cover all the execution passes. So the Concolic execution is a very useful tool, but it is slow to see the overhead. So let's consider a very simple statement where the circuit add is a arbitrary binary operation. So to symbolic execute the statement, the Concolic executor will perform the following steps. So first step is to pass the instruction, where the semantics of the operation is extracted from the code. So there are generally two ways to do this. The first way is through interpretation, and which is very slow. The second way is done through instrumentation, and it's way more faster. And it is adopted by recent works like QSYM, SymQEMU, SymCC, and also this work SymSAN. The reason why instrumentation is faster is because the parsing is done only once, either at the compilation phase or at the binary code translation phase. And there are two more overhead sources. First one is to access the symbolic expression from the symbolic state. And also we need to create and update the symbolic expression to the shared memory for the result. And according to our profiling, we find that locating, creating, and updating symbolic expressions have long trivial overhead, and this is the target problem that this work tries to solve. So our insight to reduce the overhead is pretty straightforward, because we realized that Concolic execution is just a special form of dynamic data flow analysis. So a Concolic executor can be simply implemented on top of data flow sanitizer, which is highly optimized. So to use SymSAN is quite simple. So it is similar to SymCC. So you just need to point the compiler to SymSAN, and that's it. So like SymCC, SymSAN also instrument the code in the LLVM IR level, and it has a runtime to manage symbolic expressions and connect constraints. So to see why the Concolic execution can be implemented as on top of the data flow analysis framework, so I want to go through this. So let's just compare the generic data flow analysis with the Concolic execution. So a dynamic data flow analyzer tracks the information flow between sources and things. So conceptually, a dynamic data flow analysis framework associates each program variable with a label which represents its properties, meaning how its value depends on the source. A dynamic data flow analysis framework is defined by a policy which describes how labels are introduced, propagated, and used. So it is easy to see that Concolic execution perfectly fits in this framework. Specifically, the label source are just program inputs. The propagation rules just define how new symbolic expressions are constructed based on the semantic of each instruction. The label things are just conditional branches where we update the past constraints. So, to let each label represent a symbolic expression, we just need to leverage DFSAN's union table. So each slot in this union table stores a data structure which we extend to represent the symbolic expression. So in this data structure, you only need to remember the left-hand side operand and right-hand side operand and opcode and concrete operands and things like this. So it is also easy to see with this data structure design, we're actually building a abstract syntax tree with this union table. So here's a running example. So before the execution, you can see that in the shadow memory, we have X mapped to label 101, which in this slot, it stores the symmetric expression for X. And in the next, we have another mapping from Y to 102. And you have another slot in this union table corresponding to symbolic expression for Y. And after the expression, you have new mapping, and also you insert a new slot in this union table. So that's it, very straightforward. So why SymSAN is faster? It's because it inherits all the advantage from DFSAN. So I have summarized the key factors for the performance advantage. So first of all, in SymCC, using smart pointers, which are loaded from and stored to shared memory and passed along the execution. And according to our profiling, handling smart pointers impose significant overhead. While in SymSAN, we just pass around a 32-bit integer, which is basically just index for that union table. The second reason is that for the shared memory access in SymCC, it uses tree map, and it has a long constant overhead for each access. But for SymSAN, because it's built based on DFSAN and it uses direct mapping, so it has a constant shared memory access time. And for the allocation, SymCC uses, calls a malloc, but SymSAN just kind of uses an atomic instruction. And for the argument pathing, return value pathing, SymCC uses this C++ container, and it involves multiple function calls. But for SymSAN, it just uses thread local storage, and only a single move instruction is needed to pass along the arguments. So combine all these things together, SymSAN is much faster than the existing tools. We can see that. So this result is aggregated result from running 20 real-world programs. So regarding the constraint connecting speed, you can see that SymSAN is significantly faster than the existing tools. And also, with this benefit, we can actually solve twice more constraints, giving the same time budget for each input. Another good thing for SymSAN is that the symbolic expression design is really compact. So the memory, so it consumes much less memory. So according to our results, SymSAN consumes 1 order of magnitude less memory than SymCC, which is a good thing because with this small memory requirements, we can do asynchronous solving very easily. So we kind of paired the SymSAN with mutational fuzzer, and we get a hybrid fuzzer, and we input this hybrid fuzzer to Fuzzbench, and currently we have a very good results in the Google's Fuzzbench benchmark. So next I want to talk about several takeaways. So first of all, SymSAN is a very efficient concurrent executor. It's built on top of DFSAN. And if we are trying to do a source-based concurrent execution, you should at least try our tools, which I believe we have a near optimal performance in all the source-based concurrent executors. And I'm not trying to bluff here, but if you pair SymSAN with our optimized constraint solver, Jigsaw, you kind of get a very fast concurrent executor, which is very useful, and will help this combination. SymSAN and Jigsaw become the foundation to solve many bottlenecks in the concurrent execution domain. Of course, SymSAN is open sourced. You're welcome to try our tool. And thank you very much for listening, and I'm open to questions.